Hello and welcome back to the Age of Gaming. In this small experiment that I found in the Programming a Microcomputer 6502 book by Caxton Foster, we're going to create a small music machine, basically like a keyboard or a piano. So let's just take a quick look at what this actually does so we can get into all the things that we had to do to make it work. Let's press go here, and when I press a key, and then I have to go over here to these dip switches. Now you know why I got this keypad instead of the dip switches, because it's kind of hard to move these dip switches back and forth. But adding this keypad added a few unique challenges, as it does not work the same as these dip switches at all. But we'll get into all of that pretty soon here. So anyhow, that's how the program works. You press a key and a different tone will come out of your speaker here. So let's take a look at what's going on here. Okay, this is everything that I've done to program our little piano and to explain what's going on. Here's our ribbon cable that explains, which ports are being used as inputs and which ones are being used as outputs. This is our data port and data directional registers, inputs, outputs, our status register and how that becomes important, and a simple flow chart that tells you how this program actually works. Well, all of this together looks kind of complicated, so let's break this down by simply starting off by looking at the ribbon cable. I know that everybody's going to think, well, that's just, a bunch of wires, so it's pretty straightforward, but we can really find out a lot of things what's going on by just looking at this ribbon cable and explaining everything that we know about it. Well, first off, down here we're using PA0, which is port A, pin 0 through port A, pin 7, and we're going to set them all as inputs. And those are the yellow wires down here that are going to our dip switches. Then we're also going to set PB1 through PB5, these purple wires, to be inputs as well. You'll note that we do not have PB6 or PB7. PB6 is, a long story all by itself. It's a chip select pin. It does not even come to our output edge connector, and it doesn't seem to go anywhere in the schematics that I've looked at. So that one is going to get dropped off anyhow, and since we have our 5 volts and our ground going through our cable, I decided to drop off PB7 as well, which means we're going to have to do something with those 2 missing pins. So let's get started over here. You can see your data directional registers at 1703 and 1701. So for port A, we're going to set 1701 to a 00, because zeros are inputs and ones are outputs. Now, the way they tell you to remember that is a 0 looks like an O and a 1 looks like an I, so just reverse it. But I think it's, more like the female and male connectors. A 0 is a female, an input, and a 1 is a male. So however you want to remember how inputs are set up and outputs are set up is up to you. Anyhow, so like I said, PBA through PB, or PA0 through PA7 will be all set up as inputs, but PB1 through PB5 are the only inputs that we're going to be using on port B. So there we set up a C1, which is a 1-1, which makes PB7 and PB6 an output, And the only inputs are 5, 4, 3, 2, 1 here. And we're going to be officially using PB0 here as our only true output. Okay, so now let's go back to the computer and take a look at why I have these all labeled. Like this is an 80 here. You can see the 80 on PB7, 40. It's like when you switch PA0, it shows in our port, our actual data port, will show up as a 1. And if you switch PA1, you'll get a 2. PA2, you'll get a 4, an 8, a 10, a 20, a 40, and then finally an 80. And what happens in our program is we rotate left, like this one, we just keep rotating it left until it actually gets here and becomes an 80. And believe it or not, an 80, which is a 10000000, which is 128 in decimal, is actually a negative number. So we can do a branch if minus once it hits 80. So if we have just this switch pressed, it's automatically going to branch down to, another part of our program. So let's take a quick look to see what we see when we actually switch these switches and see what's on the actual data ports themselves. Okay, now let's go to address 1700, which is our port A, and see what happens when we switch these switches. Now this is a PB7 all the way over here, and when I switch it, you can see I have an 80. Now that 80 is actually a negative number, so in our program we have that 80 branch to find the final results of what key is being pressed. And if we go down, we'll see the next key is a 40, a 20, a 10, a 08, and then a 4, and a 2, and finally a 1. Okay, so now you know what is coming out of all of these switches. Now let's take a quick look at these, because these are quite different, which provides a unique challenge. So let's go to address 1702, which is the data port B. And when we press, let's see, one of these keys, like right here, we get a 1E, a 2E, a 3-6, a 3A, and a 3C. Now those are hard to follow, using the logic of our simple switches here, but because we have, masked out, PB0 and PB6 and PB7, these are actually mass number. And if you exclusive ORed them, you would get actually 20, we would get a 10, an 8, a 4, and a 2, because that's the last key that we're using here. Okay, so that is interesting. And I guess while I still have all of this up, let's take a quick look at the status register. Now what I'm going to do is I'm going to go to address 0300, and we'll just write a simple program. We'll start with load A with a, let's say a 40 for now, and then load A again with 00, and then load A again with an 80. Okay, now we're going to go back to address 0300, put it in single step mode. Now the first one we're loading is a 40, so we're going to do that, and then we're going to go to address 00F1 and take a look at the status register, which we see is a 6C. Now that's what it's going to be a good part of the time, unless it's 0. So we're going to go back to our program counter. And I'll explain more about this, but for right now, there's our 6C. And then we're going to go back to program counter and do the next one, which is 00, address 00F1. And now we have 6E in our status register, which means that the 0 pin has been turned on. So you got a 1110 here at the end of this. Okay, now go back and one more time. And this time we should set the negative, because we have a eddy in there. So address 00F1, and now we have an EC. All right, so that's our status register. This is pretty much the 3 ways the status register is going to be set up during our program. Okay, so let's go back and finish the discussion of the ribbon cable. Okay, I think we pretty much discussed, everything we need to know about our ribbon cable. How you see an 80 when PA7 is switched on, and 40, 20, 10, 8, and also how we saw a 1E when PB5 was turned on, and that's actually equates to a 20 once we exclusive OR that. And PB4, we saw a 2E, which is a 10, PB3, 3.6, which is an 8, and finally, and PB2, 3A, which is a 4, and finally PB1, which is a 3C, which equates to a 2. Now these will, will also rotate those left until this 20 actually comes out to be an 80 in our program. We discussed the 3 different settings that our status register will show up as, and how we have the, set PB, the port B data directional register, so that we have just the inputs that we want, which was PB1 through PB5. Okay, now not everybody's going to have a ribbon cable to use that connects to their KIM-1 or whatever computer you're using. So let's take a look at what else you might be able to do. Here's, in our case, we're using the 6530 PIA chip, and we can just find out where the pins are. We're going to want PA0, which is pin 2, PA1, 2, 3, 4, 5, 6, 7, just like that. Now if you don't have a ribbon cable, I would suggest that something that's simple that you could do is have an alligator clip and have that connected on your port, and run some wires directly from that to your breadboard. Show you what that might look like. Now here I have an alligator clip connected to my 6530, and I have some wires coming right off of there and going straight into a spare breadboard that I have, to give you an example of how you might be able to set up something a little bit differently than I have. You might not have a KIM-1 or an edge connector or a ribbon cable going to a breadboard, but you could always use an alligator clip like this and have some wires going straight off that alligator clip to your breadboard. So just something, to think about if you're not using a KIM-1, if you are using a KIM-1, if you don't have, something set up already and don't want to do a whole bunch of soldering, you could always use this nifty little trick. Now we're pretty much done explaining the ribbon cable, but it's really important. Here's one more thing here. I've already explained that you had to set your port B data direction so that only, PB1 through PB5 are being used as inputs, and the other 2 or the other 3 are set up as outputs. But since we are using that really cute those button switches, they provided a unique challenge of their own because they don't work exactly like the dip switches do. They work in the exact opposite way. When you have all the buttons not being pressed, everything is a high, and only when you press a button down does a low go. But we want a high when you press the button down. So what we have to do is we have to invert that C1 in our program to be a 3E, which is pretty much just the exact opposite of our C1. But you'll see that more in the program when we do that inversion, so that when you actually press the button down, you're getting a high on your input, so everything works out. And that's where, you know, your E1 turns into a 20, a 10, an 8, a 4, and 2. So this was a unique challenge, and this is something you're going to have to be aware of in the future. XOR will basically invert whatever you have, so if you need positive inputs then and your buttons are giving you negative inputs, just do an XOR of whatever you know, whichever port pins you need to be XOR'd, and you can invert the entire thing. So let's go ahead and start looking at the actual program. Okay, well, let's first look at the flow chart of this program to get an idea of what we're going to be doing. Up here, first we're going to initialize, and when I say initialize, we're actually going to set the data directional registers here with our 0, 0 and our C1. Then we're going to go down here to first, which means basically the first set of inputs here. We're going to go to first, and we're going to set our X counter, our index counter, to 0. And then we're going to check to see if any keys in port A were pressed. If no keys were pressed, we're going to go up here to second, and check our second group of inputs. Here we're going to set the counter to 6 because this only goes up to 20, and you're going to have to, shift left twice before you get to the first digit. So just take my word, we're going to set the counter to 6. And again, we're going to check to see if any keys were pressed here in port B, and if no, we'll go right back to first. So now let's take this one step further and go down through our program. We're going to set our counter back to 0, see if any keys are pressed. If a key is pressed, let's say right now the PA7 is pressed, which is already a negative number. We're going to say, is it this key? And yes, it is that key. So then you're going to go yes, down here to found. We're going to get the delay from our index table, wait that specific delay, and then toggle our output port or our speaker on PB0, and then jump back to first. Now if it was something other than PA7, we'd go set our counter to 0, see if a key was pressed, and let's say this time it's just PA6, which is a 40. So it says yes. Well, it isn't this key. It's going to say, is it this key? And we'll say no. What we're going to do is shift that 40 up here to 80, and then say, is it that key? And we'll say yes, which is also going to increment our X counter to 1, so that when we get down here to found, get the delay, it's going to take the second set of delay numbers out of our table. 0, then 1 is our second. And then wait that delay and toggle the speaker, giving us a different frequency. And so on and so forth. And the same thing on this side. We'll set the counter to 6, see if any key was pressed, and say yes, there was a key pressed. Is it this key? It's never going to be this key right off the bat because we only start at 20. So we're going to have to shift our counter here if we have PB5 pressed, and shift it twice at least to get it to up to 80, and then it'll say yes, found. Find that specific delay in the table, and which would be about number 8, I guess, yeah, for this one, and wait that delay, toggle the speaker, and jump back to first. Okay, so hopefully I've covered the flow chart, and we can move on to the actual program itself. Now here's our actual program, and with some notes up here. The first part here, LDA 00, store that in 1701. 1701 is our port A data directional register. We're putting a 00 in it. LDA C1, which is going to set up PB1 through PB5 as inputs and store that in port B data directional register. So to initialize, we will set up port A, PA0 through PA7, and port B, PB1 through PB5 as inputs. PB0 will be the output to the speaker. Okay, now here is first. We check to see if any key is pressed in port A. If port A is not all zeros, we will shift left and count by indexing the X register to see which key was pressed. Then branch to found once the correct key has been indicated. If no key is detected in port A, we will branch to second. So here's first. First thing we're going to do is we're setting LDX to 00, that's our index counter. Then we're going to LDA 1700, which is load our port A inputs into LDA to see if what's being pressed. I have EA here in case we added a second set of buttons and had to do the EOR for that, but since we don't right now, that's just EA. So this is unnecessary right here. So the next command is branches if equal to second. What that actually means is branch if it's 0 to second. So that's what it would do. If nothing is pressed, it's going to come down here to second. Now, if something is pressed, if there's something in here, it's going to jump down to here, branch if minus to found. Well, unless it's PA7, which is an 80, we're going to come down here and increment X. We're going to shift left and come back up here and then see if we found the right key yet. If there was a minus, if it made it to 80. If it did make it to 80, it would go down here to find or found and complete that program. And it would just keep doing this loop until it does finally get to a found. Like if we press the first key and it's just a 1, it would loop through here like 7 or 8 times before it got to found. Now, if nothing was pressed here, we jump down to second. Second, we're doing pretty much the same thing. We're going to load X with 06 this time because we want the table to start at like number 8, and the first key that you can press on PB5 would take 2 shifts to get up to an 8. So we're going to load A with port B data, which is PB1 through PB5 input data. And I found out we don't have to do this AND. So I put an EA and an EA there because it's already been masked, so we don't need to mask it again. But what we did need to do, because of our buttons and the way they work, I had to EOR the contents of 1702 so that we would get the right inputs when we push the buttons. And then again, we're going to branch if equal. I mean, if there's a 0 in there, then we're going to jump right back up to first. If something was found, automatically we're going to have to, it's never going to be found right away. We're going to have to index X from 6 to 7 and then to 8, even if it's PB5, and keep indexing until we find which key, until it actually sums up to 80. And then it's going to come down here to found. Now in the found portion, we are basically loading our table here. We LDA X, which is our table, which is here at 0240 or 240. We're going to start loading the table plus whatever X is. So we're going to go to 240 plus whatever X is. If it was PA7, we would get this D9 here. Matter of fact, these are pretty much all PA inputs until we get down to here where your PB inputs will get their delay information from. So we're going to load the table, whichever table entry that we're currently on. We're going to transfer that to Y, and then we're going to decrement Y and keep branching, keep decrementing until that delay is complete. And then we're going to toggle 1702, which is the B port, and what it's going to do, it's going to toggle pretty much the last bit from a 1 to a 0 and a 1 to a 0 and a 1 to a 0, and basically just keep, you know, creating a square wave for you. And then we'll just jump right back up here to first and go through it again. So hopefully that explains everything. If you have any questions, don't hesitate to ask. And have a great day. Thanks for watching.